This lesson is from 10.4 of your textbook, and it discusses some of the applications of radian measure and angles. The first of which is to talk about the length around, or the circumference, or even just a part of the arc, and the area of what's called a sector. So if we look at a circle, you've probably seen these formulas before, but if you're referring to a circle, you know that the circumference is equal to 2 pi r. So that would be the entire angle, 2 pi, if you were to go all the way around the circle, times the radius. And the area for this circle is pi r squared. So that works for a whole circle. What happens if we just want part of the circle? So suppose that we want to look at what's called a sector. And the sector is what we have shown here. It looks kind of like a piece of pizza or a piece of pie. If you were to cut into the center with 2 radii, and then you would have what's called an arc length, which is S. And the arc length would just be a fraction of the circumference. And that fraction would be based on the angle that is in the center here. So the arc length is actually pretty simple. It's very similar to the circumference formula. It is just theta times r. So in this case, for a full circle, the whole angle was 2 pi times the radius. So for any sector, whatever your angle is, you can plug that in times r. So like I said, this is what we call arc length. And the thing to be very careful with here is that theta is always in radians. So that's one thing that we need to make sure of, and that's why radians are important and are helpful, is because that angle must always be in radians. If we wanted to find an area of a sector, so I'm going to put a little subscript s there to describe the sector, then again we want to find a fraction or a portion of this. And it's not quite as easy to see the relationship here, but it's not too hard to see. If you look at the circle here, we have pi r squared. The r squared is going to stay the same for our equation. The difference here is looking at what this angle is. And essentially pi is half of the angle that you would take to get all the way around the circle. You would take 2 pi to get all the way around the circle, so pi is half of that. So if you can kind of remember that, then the area for a sector is 1/2 of whatever angle is inscribed there times the radius squared. So again, we get the same type of formula. It's just we've got to be careful. We've got half of the angle in this case. Again, theta must be in radians to do this calculation. So make sure that you're doing your calculations. Sometimes the angles will be given in degrees, like the next example I have written there. And so we need to convert them to radians. So we'll discuss how to do that again. So if we look at this first example, we want to find the length of the arc of a circle of radius 4.5 centimeters and central angle 135 degrees. So, like I said, we always need to make sure that theta is in radians. So if it's 135 degrees, then to change that to radians, we're going to multiply by pi over 180. And you should remember this from the first lesson in 10.3. So if you do that simplification, you should get exactly 3 pi over 4. And if you wanted an approximation for it, which I wouldn't recommend using because it's going to throw off your calculations, but the approximation for this would be 2.356. And again, essentially all you have to do is reduce the fraction 135 over 180, you get 3/4, and then you've got that pi. So you get 3/4 pi. So now if we want to find the length of the arc, so the arc length, S, is going to be equal to we have the formula here, theta times r. So in this case, theta is 3 pi over 4, and our radius, we said, is 4.5. So again, we can keep this as an exact answer if we just multiply the whole numbers and forget about pi. And if that's the case, then we end up with 27 pi over 8. And again, you can find the fractions by using the math frac button in your calculator. So for instance here, I would say 3 times 4.5 divided by 4, and I'm not worrying about the pi, and I get that 3.375. If I hit math, and then that first option is frac, then I will get the fraction equivalent of the answer. So I get 27/8, and then we have that pi there, which goes in our numerator because it was a multiplication. It was already in the numerator. So this is the arc length. If we wanted an approximation, we could find that. If we wanted to find out how much string or whatever was going around it, and we would say that this is approximately 10.6 centimeters. And we always want to make sure that we remember our units for these. Looking at the next example, which is based off of the same dimensions, we would now want to find the area of that sector. So we want to find the area of the sector of a circle of radius 4.5 centimeters and central angle 135. So we already said that this angle is 3 pi over 4. So then we can go back up to our area formula, which is 1/2 theta r squared. So we plug in 1/2. Theta is 3 pi over 4, and our radius is 4.5, and we square it. And we're very careful about how we put this in the calculator. I'll show you how to do it, for example. We've got a bunch of fractions here. We've got 1, and we want to make sure that we put them in parentheses. So 1 divided by 2 would be our first fraction, 1/2, times, we can think of this as 3/4 because there's that pi. So 3 divided by 4. And then we've got times 4.5 squared. We hit enter, and it gives us this kind of nasty decimal. If we want to try to find the fraction, it's not real pretty either, but we'll write it down. 243 pi over 32. So that would be the exact answer. If we wanted to find the approximation, we can just hit times pi, and then we will get the approximate answer for our fraction there, which is 23.86. And again, we need some units here. In this case, we're finding an area. Our original dimensions were centimeters, so we are going to have centimeters squared. We can also look at these sectors and as lengths. So when we talk about things that rotate, we can talk about the length that they travel linearly. If you think about a tire, it's transforming rotation into linear speed and movement because you're moving the car along a road and not around a wheel. So if we look at a car tire, for instance, it has a loaded radius of 13.1 inches. So we're saying that the car with the load on it, on that tire, is 13.1 inch radius. How far does the car travel in 100 rotations of the tire? Well, this is actually pretty easy because we just really need to find the circumference of the tire. So the circumference of the tire in this case is just the angle, which for a full angle would be 2 pi, times our 13.1 inches. So if we do that multiplication, we end up with 26.2 pi, or approximately, if you want to put it in the calculator, because that might make a little bit more sense. (82.31 inches. So in one rotation of your tire, if you had these tires, you would go 82.31 inches. Woohoo, real far, right? So we want to know what happens in 100 rotations. So that's pretty easy. Then all we have to do is, so we need 100 rotations, is going to just be that 82.31 times 100. And one of the nice things about multiplying by 100 is all we have to do is move the decimal points the same number of zeros. So we can move that decimal point over 2 places, and we end up with about 82.31 inches. So that doesn't really tell us a whole lot. Okay, yeah, we went 8,231 inches. What's that mean in feet or miles or whatever? So just to kind of refresh our memories on unit conversion, remember that there are 12 inches in a foot. So if we wanted to do this conversion, we would say, okay, well, we know that there is 1 foot per 12 inches. Whatever we want to get rid of here is whatever is going to go in the denominator, so it can cancel out. just like we did with the angle in the previous problem. So if we have our 8231, so I'll multiply by 100 here, and then we need to divide that by our 12. So 685.9 feet. That's a little bit more helpful as far as telling us how far we've gone. We could convert it to yards. As far as miles go, just to kind of let you know, we can do one more conversion with it. There are actually 5,280 feet in a mile, so 1 mile, if we wanted to convert it, would be 1 mile to 5,280 feet. And the trick that I was told to remember that is 5 tomatoes, 5280. So again, all we would have to do, we already have that number in there, we would divide it by 5280, and it would tell us that we've gone about 0.13 miles. Again, it just depends on what it is that you are trying to figure out, what's the most useful unit for you. And as long as you label what the unit is, then you're fine. You just need to make sure that you are labeling it with the correct unit and that it's the one that's most useful for you. So, if we look at another example, I want you guys to take a second, pause the video, and see if you can try this next example. It says an airplane travels in a circular path around an airport at 500 miles per hour for 6 minutes. How far from the airport is the plane, i.e., what is the radius of the circle, when the central angle is 195 degrees? So think about that for a few seconds, pause the video, try to work this one out, and then resume the video when you figured it out. So this example is actually kind of the opposite of what we did in the last one. And we again have to be careful with our units here. We have 500 miles per hour in 6 minutes. We've got hours and minutes, so we need to make sure that we're very careful with that. So in this case, we've got the linear distance that the plane has traveled, because we can figure that out based on the rate and the time, because distance equals rate times time. And we know the angle is 195 degrees, so we'll have to do some conversion to radians there. So based on those two pieces of information, we can go backwards and find the radius. So first things first, the easy one, let's convert the 195 degrees to radians. So we multiply by pi over 180, which would be 13 pi over 12. It's a little bit easier to deal with than the decimal, that approximation that goes with it. The other thing we need to do is actually figure out the distance. So we said distance equals rate times time. In this case, we've got a rate of 500 miles per hour. And we've got a distance of 6 minutes. So we need to convert this to minutes. So we say that there is 1 hour is 60 minutes. Since it's in the denominator, we need to put the hour up top so that it'll cancel in the fraction. And then to get rid of the minutes here, we would multiply by our 6 minutes, because then that will get rid of our time unit and we'll be left with the distance in miles. So in this case, distance is equal to, if you multiply your 500 times your 6 and divided by 60, you are left with 50. That's pretty reasonable. So we've gone 50 miles in those 6 minutes. That's pretty fast, right? So we got a distance of 50 miles. We've got an angle of 13 pi over 12. So we just set up our equation. We say, okay, distance or arc length in this case is equal to the same thing, theta r. So we know the distance was 50. We know the theta was 13 pi over 12. And we want to find the radius. So all we have to do is we can multiply by 12 over 13 pi to get rid of that fraction. So we multiply on both sides by that 12 over 13 pi. And we will get our answer. So we end up with 50 times 12 divided by, and we're very careful here to put in parentheses the denominator, because we would need to make sure that they are both in the denominator, not just one of them. And then we can hit enter and we end up with approximately 14.7 miles. So that is the distance between the actual airport and the plane, but it's traveling outside on this circle. So those are distances. We can also talk about velocity and speed, and we can talk about them being angular and linear. So we already kind of discussed it in that last one. When we talk about linear speed, we're talking about just the straight line distance per unit of time. So what do we mean when we say angular velocity? Well, the angular velocity actually measures the change in the angle over time. And we use the letter omega. It looks like a W, but it's a Greek lowercase omega. And we say that this is the change in angle over time. Depending on the context, a lot of times these angular velocities are given in revolutions per minute. If you've ever looked at the tachometer on your car, it'll give it in revolutions per minute. And what's helpful though when you're doing some of these calculations is you really need to go back to radians per minute or radians per second. So again, there's going to be some unit conversions with this. Omega is always given in radians per second. So we need to do some conversions between that. Linear speed can be given in various units, but usually we give it the letter V, and we say that this is the change in distance over time. I'm going to put a little symbol in here that I forgot about, which is delta, meaning change in distance over change in time. So it's not just a specific point, it's how it's changed from the start to the finish. And again, this is usually, it's measured in various things. It depends on if you're in metric or English. Sometimes it's in feet, sometimes it's in meters. Meters per second is relatively common, or miles per hour is one that's common in the US. The other thing to keep in mind is how these two things are related. So we already said that the arc length, is equal to the angle times the radius. Well, if omega is the change in angle over the change in time, and we want to find the velocity, then we can do the same thing here. Velocity is going to be omega times r. So it's very similar. The only difference here is now we've got a change in time, where omega is change in angle over the change in time. So let's do some examples with this. Suppose you have an airplane propeller whose blades are 6 feet long and it's rotating at 2200 RPM. That's pretty quick. Express this at an angular speed in radians per second. So we're going to do this step by step. We're going to look at this 2200 RPM and we are going to convert that to radians per second. So first thing, you start with your 2200 RPM. Let's say that this is omega. I'm going to rewrite the RPM as what it actually stands for, which is revolutions per minute. And we want to put it in radians per second, meaning first thing, let's get rid of this revolution. So think about this for a second. How many radians are in a revolution? One full revolution is all the way around the circle. So then 2 pi radians would be in one revolution, all the way around the circle. So that will get rid of our revolutions. And then we've got to get rid of the minutes. So we want to convert that to seconds. So we say, okay, well, 1 minute, and again, we always put it on the opposite side of the fraction bar so we can get rid of it, per 60 seconds. So that will get rid of the minutes. And maybe I'll use a different color so that we can see that those cancel that way. So in this case, if we wanted to put this into our calculator, again, I would kind of avoid putting in the pi if possible, but we have 2200. Anything else on the numerator, we have a 2 pi, so we'll do times 2. And then we're dividing by, it looks like the only number we have other than 1 is the 60, so then we're dividing by 60. So this gives us this fraction here. If we wanted to, we could convert it to a fraction, which is 223 thirds, and we still have that pi up top. So this is our angular speed, our exact angular speed, which is 220 pi divided by 3. If we wanted to, again, we could just multiply by pi to get our approximate answer, which is 230.38. And again, we've converted this to radians per second. So this is one of the rare cases where you actually see radians given, and the only reason is just because it makes it a little bit easier to see the units. Okay, so then we move on to part B. We want to find the angular displacement at 3 seconds. So the angular displacement means how much has the angle changed. So in this case, we want to find theta, which would be our change in angle, which is the if we write it as omega times t, we're just rearranging that formula for omega being the change in theta over the change in time. So in this case, we've got omega is 230.38 radians per second, and our time we just said was 3 seconds. And so that's why we wanted to convert it to radians per second so we could do this part of the problem. So now we take our answer, and maybe we should have used actually the exact version, the 220 pi over 3. If you were to find the exact in this case, it would end up just being 220 pi because the 3 up top would cancel with the 3 in the bottom. If you wanted to find the exact answer, you could just take that 230.38 and multiply it by 3, and you get 691.2. And again, now we've converted it to just radians. That's our angular displacement. The seconds here cancel out with the seconds there. The last part of this question says we want to find the linear speed of a point on the end of the blade. So the point on the end of the blade, if you're thinking of this more as being a wheel, how far would it have traveled, whatever vehicle it was, if you had actually put this thing on the ground and let it move. So in this case, we need that piece of information up here, which is that it was a 6-foot long propeller. So now we take we just want to find the linear speed. So we have our omega v equals omega r. So we've got omega, which was 220 pi over 3, and this is radians per second. And we are multiplying then by our distance, which is 6 feet. And since radians are technically considered to be unitless, we don't have to worry about them in the final answer. So the 6 and the 3 would simplify to be 2. 2 times 220 is 440. And then we have our pi. If you wanted an approximation, you could just go in 440 pi, and you would get that approximation of 1382.3. And again, our units this time now are feet per second. So it would really depend on what you wanted your final answer to be in. If it wanted to be feet per second, inches per second, miles per second. So you would need to make sure that you don't have to do some final conversions at the end. I'm going to try one more example here with you, and then I'm going to have you guys work one. And sometimes, the one thing I want to point out here is that sometimes only part of this question is given. They might only say to find the linear speed of the point. You'd have to go back and actually remember that you have to find the angular speed first and then the linear speed, because we always have to convert RPM to a usable unit, which is radians per second. So it's possible that all 3 steps might not be listed here, and you need to go back and figure out which steps you need to get to the problem. So example 27 looks at a much larger example. Look at the Earth revolving about the sun. And I know that the Earth is actually in an elliptical orbit, but it's very close to being circular. And for many years they thought it was circular. So we're going to go with that assumption just to make things a little bit simpler. So suppose it's on the basis of 1 revolution per year. It's actually about 365¼ days. That's why we get leap year. Assume that an average circular orbit of the radius is 1.5 times 10 to the 8th kilometers. We want to find the linear speed in kilometers per second of the Earth around the sun. And in all honesty, this is very close to just being a unit analysis problem. If you can get really good at dimensional analysis and converting units, then problems end up being a lot easier a lot of times. And essentially that's what we need to do here. We want to find the linear speed in kilometers per second. We've got kilometers and we've got this unit of time. So let's look at that. So V equals omega r. Well, we can find the angular speed because we know that omega is equal to 1 revolution per year. We want our final answer to be in seconds, so we'll do some conversion there. We know that a year has 365.25 days, which is what I gave you. We know that a day, so we're trying to get rid of that, is 24 hours. We know that an hour is 60 minutes, and we know that a minute is 60 seconds. So all of this ends up being a rather large number on the denominator, and I'd kind of like to just keep it as the large number on the denominator because it ends up being 365.25 times 24 times 60 times 60. And this ends up as this really large number here in the denominator, which is 3155,7600. So 31,557,600. And this is the denominator. So 1 revolution per that many seconds. So the one thing that we forgot about is that we need to convert this then to radians. So we need to convert the revolution. So 1 revolution is 2 pi. So this ends up being 2 pi over our 31,557,600 seconds. So we found our angular velocity, and now we just need to plug it in up here into our linear velocity. So 2 pi over 31,557,600 seconds times our radius, which is 1.5 times 10 to the 8th kilometers. And if you don't remember how to put this times 10 to the 8th in your calculator, I'll show you right now. So we have 2 pi divided by, and I'm just going to hit answer because we already had that large number as our denominator. And so this is our angular velocity. Now we need to multiply that by 1.5. And what you want to use is this EE here, this capital E, capital E. So we're going to hit second and then that. It'll only show up one E, and that's fine. That's just to save screen space, but it's doing this operation. That's the times 10 to the. Do not put 10, only put the exponent. That's what the E stands for, is it's your exponent. So when we hit enter here, we end up with 29.87 kilometers per second. Now just think about this for a second. A kilometer is roughly 0.6 or 6/10 of a mile. And if this is the case, if we were to look at this, so this is 0.6 of a mile, think about how fast that is going in miles per second. Think about how fast we are actually going around the sun, and we can't feel it at all. So it's kind of cool to kind of think about how fast we're actually moving, but thanks to gravity and just our sense of already having been on the earth for our entire lives, we're just used to it. So there's one final example here, and I want you guys to try it out on your own and then pause the video, try it out, and then resume the video when you're done. And I'll have the answer up here and we'll talk about it. So pause the video now and see how you do. So to wrap this one up, answer the following questions based on the given information. An engine flywheel is rotating at 400 RPM. First thing we want to do is convert it to an angular speed of radians per second. So we're going to do the same thing we did in example 26. We're going to multiply by 2 pi radians per revolution, and then 1 minute per 60 seconds to convert that, get rid of that revolutions, get rid of that minutes. And in exact form, we end up with 4 pi over 3 radians per second. Second part asks for the linear speed of the point on the edge of the wheel with a radius of 7 inches. So it's a pretty big flywheel. We end up with a velocity is equal to omega times r. So our omega was 4 pi over 3. Our radius is 7. So we end up with 28 pi over 3 inches per second. If we want to find the angular displacement of the wheel after 5 seconds, well, then we say, okay, we had our theta is equal to omega times time. So we've got our 4 pi over 3 radians per second times our 5 seconds, and we end up with 20 pi over 3. In this case, it's just radians, so we usually don't write any units there. The last part of the problem, you can actually do two different ways. Find the linear displacement of a point on the edge of the wheel with a radius of 7 inches after 5 seconds. One way is to look at the linear speed, and distance equals rate times time. So we take our 28 pi over 3 inches per second times our time, which was 5 seconds, and we get 140 pi over 3. The only reason we could do this was because it was the same radius. The other way we can look at it is with the arc length formula. You found your angle was 20 pi over 3, you multiply by your radius 7 inches, and again you end up with 140 pi over 3 inches. So there's two different ways that you can look at that last part of that problem. So this concludes the video for 10.4. Go through and do the homework examples from this problem, and then once you're done with all of the homework from Chapter 10, go on and do the Chapter 10 quiz.